Stripping down science. The Naked Scientists.
Hello, it's Sunday the 29th of May. Welcome to The Naked Scientists. I'm Chris Smith. This week, what do you get if you mix a blacksmith with a metallurgy research scientist?
The oranger it is, the softer it goes. Now when I hammer it, it's going to be easier to handle.
Iron's got this really unique property that at about 700 Celsius, it transforms from being one crystal structure to another. So just using the skill of a blacksmith, Gordon's managed to control the atomic structure of a piece of iron. Really amazing skills.
We're also off to Rolls-Royce to find out how they make the materials that can withstand one of the harshest environments known, the inside of a jet engine. And how do you measure the shape of something less than a billionth of a millimetre across? Well, UK scientists have done just that this week, but what is it that they measured? Find out shortly.
The Naked Scientists podcast is powered by UK Fast, the UK's best hosting provider. On the web at ukfast.co.uk.
And up first, to take a look at the latest scientific breakthroughs, is Diana O'Carroll.
Yes, well, researchers from Ontario this week have identified which parts of the brain are involved in human echolocation. Traditionally associated with bats, whales and sonar, echolocation is a technique used to find one's position by bouncing sound off surfaces and waiting for the echo. The study, performed by Law Thaler and colleagues at the University of Ontario and the Rotman Research Institute, compared the brain activity between two study subjects. One had been blind since 13 months and the other had developed blindness in adolescence. Both these individuals used clicking sounds made with their own mouths to glean information about their surroundings, and both blind subjects were able to tell when a panel placed before them was flat or concave and whether it was 20 degrees to the right or left. Outdoors, they could tell if they were standing in front of a car or a tree or a lamppost, but the researchers had to overcome the problem of echolocating inside the brain-scanning fMRI machine, where it's noisy and there's nowhere to go. So what they did was to pre-record echolocating sounds from microphones at the subject's ears, and then they played the recording back to them inside the machine. Publishing in PLOS ONE, they found that in both blind subjects, the calcarine cortex, an area of the brain normally dedicated to processing visual information in sighted people, displayed greater activity when the subjects listened to the echo sounds. Now, this implies that they could see something from the sound of the echoes, and this was compared to fairly constant levels of activity in the part of the brain typically used for processing auditory information, and that's when they listened to the echoless clicks. So it does look like they're seeing with sound rather than hearing.
And it does gel with what we've known before about the fact that people who are blind seem to use the vacant brain processing areas that would normally subserve vision, and they do other tasks of processing sounds and other things, and maybe even texture with those brain areas. And so that kind of fits with that too. Yeah,
I mean, it's incredible how their brains have rewired in this way. But I think it's important to point out that not all blind people can echolocate, and these are two very special individuals.
So these people were doing this consciously, they were making sounds, but is it not possible, therefore, that people who are blind are just subconsciously making use of echoes just coming back incidentally from the environment, and they're building a visual picture using sound like this in their minds without even realising it?
Yeah, of course, I think that's perfectly possible.
Well, also this week, and moving into physics now, scientists have come up with an attractive new magnetic material. This is actually the work of Tomoteru Fukumura, who's a researcher at Tokyo University. And what they've been able to do is to produce a substance which, when you apply a very small voltage to it, becomes a permanent magnet, temporarily. Now, the reason for putting it like that is that for many years scientists have known that it's possible to take a material and make it so that you can apply voltage to it and therefore make it behave in a magnetic way. But the problem is the materials they'd succeeded in making were all only active at very low temperatures, close to absolute zero. The amazing thing about this new chemical is that it has this interesting behaviour at a very high temperature, room temperature. Now, what the scientists did, they were using titanium dioxide, which is the same stuff you use to make paper go white. You make paints with titanium dioxide. So it's an interesting material in itself. But they added to it about 10% cobalt ions. And what happens is that in the crystal lattice that the titanium dioxide would normally form, about 1 in every 10 of the atoms are substituted by cobalt. Now, cobalt is a ferromagnetic material. So what this does is to turn the titanium dioxide into what's called a paramagnetic material. In other words, if you put it in a magnetic field, it will feel a force and try and move. But then if you apply an electric charge, then it behaves like a permanent magnet. And what the researchers have found is happening is that when you push the electrons into the substance, they make the spin on the electrons of all of the cobalt atoms line up in register, and the free electrons tunnel between each of the cobalt atoms, telling them what spin orientation to be in so that they all line up like this, and they stay that way until you take the current off. And so this is an amazing way of making a permanent magnetic type material, and you can make it switch on and off. And the possible applications of that are you could make a miniature transistor because you have a way of allowing current either through or not through in that way. But even more exciting, when you reflect light off of a magnetic surface, then you can actually rotate the plane of the polarization of that light. So what you could do is if you had a polarizing filter in front of some of this material, you then put some polarized light into it. By turning the magnetic field on and off, you could very quickly and very rapidly alter the amplitude of the light that was coming back off. And you could use that to, for instance, very rapidly put pulses of information down fibre optics and dramatically increase the data rate that you were downloading the Naked Scientist podcast with.
But this all sounds quite nanoscale. How big can they make this?
Well, the thing is that you can just make a crystal of the material. You take the titanium dioxide, you put in the cobalt, and so you can make sheets of this very, very easily. That's published this week, by the way, in the journal Science.
Right, well, speaking of electrons, what is round and measures 1/1000th of a millimetre across? Yes, you guessed it, I gave it away. It's the electron. Now, theories have predicted that these particles should be spheres, but proving this has been tricky. Now, after 10 years of trying, a team at Imperial College London have succeeded, as Johnny Hudson explained to Chris.
So what we've been working on is we've been trying to measure the shape of the electron. The conventional theories suggest that the electron is round, like a point particle, but we've been wanting to check that and to see whether it really is round.
Should that really make a difference?
Yeah, it's important actually, and the reason it's important is because although our sort of current theories predict that the electron should be round, some of the advanced theories that go beyond that predict that it won't be round, that it'll have a distortion. And so by doing this measurement, we look at it as a way to search for physics beyond the physics that we know about at the moment.
And just to give people some grasp as to the scale of the problem that you're grappling with, how big is an electron?
The size of the electron, it depends how you measure it. The classical, what they call the Compton wavelength, is one measure of the size of the electron, and that's 10 to the minus 12 meters, so 1/1000th of a millimeter.
Pretty small, in other words. How on earth do you go about trying to size up something like that?
If the electron were perfectly round, when we put it in an electric field, it would just spin around its axis in a perfectly regular kind of way. Whereas if it's not round, when we put the electron in the electric field, it'll develop a kind of wobble, a very distinctive kind of motion where it's kind of wobbling around its axis, a lot like a little, if you were to put a gyroscope on a stand at an angle, that kind of wobbling motion. And so we look for that wobbling motion.
Is that because the electron itself is an electrically charged particle? So if you have something which is electrically charged moving, and it's moving in an electric field, therefore the two fields are going to interact, and that's going to impart a movement on the particle that you can then pick up?
Yeah, that's basically it. If the electron were round, then it wouldn't matter which way it was oriented with respect to the field, because it would just look the same. If you turn a perfect sphere around a bit, it looks the same. Whereas if the electron, say if it were egg-shaped, if it had a bit of distortion to it, it matters which direction it's pointing in relative to the field, and so that there's a force on it trying to align it with the field, and it's that force which creates the wobbling motion.
So how did you actually do it?
Yeah, so what we do, we don't just use a bare electron, because there are some real technical difficulties with working with electrons, namely that they're electrically charged. So what we did instead is we used the electrons in a particular molecule, a molecule called a terbium fluoride. And this molecule has an unpaired electron orbiting around the outside of it, and that's the electron that we studied. And what we look at is if the electron isn't round, it starts wobbling in its orbit around the molecule. So actually what we really look at is we look to see how the molecule spins.
And what do you find?
What we find is, as best we can tell, and we've looked really very carefully, there's no wobble. The electron shows all signs of being round at our current sensitivity.
So that means, or that must have quite big implications for other things in the quantum realm then?
Yeah, like I say, our current theory of physics predicts that the electron should be really almost exactly round. And so the first thing to say is our work doesn't contradict our current theory of physics, which was, I guess, a disappointment for us. It'd be much more fun if it did contradict the theory, but you can't have everything. What it does do is, if you look at some of these theories, I said people propose these theories that go beyond our current theory of physics. Some of them predict that the electron should be really quite distorted. And actually, we've shown that it's rounder than some of those theories would predict. So what it's allowed us to do is it's allowed us to constrain and guide the development of theories that go beyond our current theory of physics. It places limits on what theories could possibly be right.
And do you think all electrons are made equal? And what I mean by that is, in the context in which you studied the electron, it behaved like that. But what would happen if you took a different molecule as the donor and studied that? Do you think you might be able to get an electron that was distorted?
Oh, no. There are no forces in the molecule that can distort the shape of the electron. This is what we're measuring here, is how the electron comes from Mother Nature. It's not the molecule itself is not placing any forces on the electron that are distorting it.
So you've nailed that one, myth busted. But are there any actual physical applications, now you are armed with this knowledge, that you can use to take this forward?
Well, one thing that physicists are very interested in is there's a big mystery in cosmology, a big mystery in describing the origin of the universe, and the mystery is what they call the matter-antimatter imbalance. So our current theory of physics, the best one we have, says that in the Big Bang, matter and antimatter were created in equal measure. And further, our theories of physics say that the laws that govern antimatter are basically the same as the laws that govern matter. And so the logical conclusion would be that we should have an equal amount of antimatter and matter today. But astronomers have looked, and you can search the skies, you can look wherever you like, you find only incredibly tiny traces of antimatter. And so this is a big mystery for people. And now one potential solution is that there's a slight difference in the behavior of matter and antimatter. And this would mean over the billions of years that the universe has existed, it could tip the balance and the matter could start to dominate over the antimatter. If the electron's not round, then you can show that it's not possible for it to behave the same as its antiparticle, the positron. So if the electron's not round, this would indicate that there has to be a difference between the behavior of matter and the behavior of antimatter. And so that's one of the motivations for studying this. People are looking for a difference between the behavior of matter and antimatter. They think there must be one that we haven't discovered yet.
So could you take your technique and apply it to the antihydrogen that has been successfully made at CERN and ask that very question?
That would be a fantastically interesting experiment, but I would say our experiment was so difficult that it took us over a decade of extremely hard work to do. Their experiment is so difficult that it took them over a decade. If you sort of multiply them together, I can't even begin to imagine how difficult that would be.
Johnny Hudson from Imperial College, and amazingly, Diana, the precision with which they say they've made those measurements is equivalent to, were you to scale the electron up to an object the size of our solar system, their measurements are precise to within the thickness of a human hair. Amazing piece of work. It's published this week in the journal Nature.
Okay, that's sort of blown my mind a little bit. Right, well, also this week, researchers from Norway have reported that people who take part in or attend cultural activities tend to have better physical and mental health.
Must explain everything about me.
Yeah. And cultural activities are defined as creative, so they can be playing music or drawing, and they're also defined as receptive, so that can include going to the theatre, a museum, and watching sports, interestingly. Maybe it depends on the sport. But publishing in the journal Epidemiology and Community Health, Konrad Kuipers and his team sent surveys to tens of thousands of people in a rural region of Norway, asking questions about their activities, their happiness, and their perceived health. The researchers then took the results, ran some statistical tests, and found this association between cultural activities and health. Now, Kuipers, who's from the Norwegian University of Science and Technology, found that it was especially men in whom this relationship was most apparent. More than females, males reported higher levels of satisfaction, happiness, and better perceived health if they took part in the receptive activities, such as watching sport or going to a museum. Now, they also found that people in lower socioeconomic groups were less less likely to attend either type of cultural activity, and that women were especially happy if they took part in more creative forms of culture. In addition, people tended to take part in more cultural activities the older they became, up to their 40s, when it started to decline again. And the researchers stress that they can't identify a causative relationship, and they don't know if a bit of culture makes you happier, or if happier and healthier people tend to involve more culture in their lives.
I was just going to say, because the kind of people you're describing, higher social class demographic, they're likely to have more disposable income to spend on availing themselves of these cultural pursuits, and therefore they might be happier because they're less stressed about how they're going to pay their mortgage, rather than the fact that doing those things makes them happier. Or did they control for that?
I don't think they're controlled for that, as far as I know. But that's a thought that occurred to me as well, because they do see this rise up until the 40s of people participating in cultural activities. And so if you've got more money, you're more likely to be able to do that. And obviously, you're more likely to get more money as you get older. So it does kind of fit in with that.
Another epidemiological study I saw recently, looking at men's happiness across their lifespan, showed that actually you're happiest at the extremes of your age span. So young men and older men tend to be at their happiest. So the grumpy old men idea is perhaps wrong, but in the middle years, actually it's like a sort of smiley face, ironically, and the down in the mouth, the lowest point where you're unhappiest, is actually coinciding with your 40s, because that's when the time when people tend to have the biggest financial burden and the most stress in their life, and kids, and therefore probably the least sleep.
So that's the midlife crisis, where they go out and buy a motorbike and grow long hair.
Exactly right, yeah, it certainly is. Well, one other thing that might happen to you in your 40s, if you're unlucky, is you might end up with your arteries becoming furred up and have to have something done about it, because this does happen to men, and it happens at a younger age than it does in women, and therefore is an important health problem. But although we've managed to bring the field of arterial surgery, if you like, and bypass grafting enormously forward in the last 20 years or so. And what I mean by that is that if you'd had, say, chest pains and angina or a cardiac problem in the 1980s and the 1990s, the treatment you probably would have received is an artery bypass graft, where they would have opened up your chest and put a piece of blood vessel around a blockage to a coronary artery. That all changed in the late 90s when interventions called PCI, percutaneous coronary intervention, came in. The idea is you thread a catheter up through an artery, go into the coronary arteries that supply the heart, put some dye down the artery, use x-rays to see where the narrowings are in the arteries. You then inflate a balloon inside the artery, opening it up, and then you prop it open with a little metal cage called a stent. That's pretty standard now, and it's totally revolutionised the treatment of heart complaints. The problem is that sort of imaging with dye and x-rays has a number of problems. One is ionising radiation, which is not all that good. But two, the dye is also bad for people who have a kidney problem or diabetes in the first place. It doesn't do much good to your kidneys. But also, it only tells us about the structure of the artery and where they're narrowed. It doesn't tell you anything about whether those bits of narrowed artery are getting a lot worse a lot quicker, or whether they're just stable and could actually be left alone and there are trouble spots brewing elsewhere. But now there's a paper this week in the journal Science Translational Medicine. It's by Farouk Jaffer and his team. He's based at Harvard University. And they wondered whether there were any chemicals or dyes or substances that could be used to see where the hot spots or the trouble spots could be brewing in the walls of arteries. So they took a look at what's already being used medically, and they found this stuff called indocyanin green. It has a very long, complicated chemical formula, but it's been used for over 5 decades quite safely. It's FDA approved, and it's used for imaging blood flow in various organs. And it turns out it's very lipophilic. It likes fatty stuff. So it looked ideal. And so they started doing some tests in experimental rabbits, and they found that when you put this into the rabbit, it will go into fatty deposits in the walls of arteries, and it seems to preferentially localise into the areas where those deposits are showing signs of being most unstable. And the added bonus here is that it can be detected by near-infrared radiation. So in other words, it emits and absorbs signal in the near-infrared regime. So you can detect where it's gone in the wall of a blood vessel by threading a little probe inside the blood vessel and then just pulling that probe back along the inside of the wall, recording the tracings. And in studies comparing ultrasound of the vessel and X-ray imaging of the vessel, and also gross histopathology of rabbit aortas that they've done these tests on, it matches up very, very well. And because it's already safely been used, 5 decades of safe use, no reason why this couldn't go into the clinic tomorrow.
And it means you're not using ionising radiation as well to do this.
Exactly. So it should be a lot better for a number of different reasons.
Yeah, just one thing. I mean, how come it was used for 5 decades and no one really noticed that it might be useful for this? Why do you think?
It's a classic example of a solution being under your nose without realising it, and it's because people have done various anatomy and pathology studies now and said we're beginning to realise that not all narrowed arteries are made equal, and there are some bits which are carrying a worse prognosis than others. Now we need to find a way to image those and identify where the hotspots are. They then went saying, well, what can we do that with? And this substance appears to fit the bill.
Lifting the lab coat on the world's best science. The Naked Scientists.
You're listening to The Naked Scientists with Chris Smith and with Diana O'Carroll. Earth observation from satellites is an extremely important way of examining everything from glaciers to tree cover in the Amazon. But sometimes satellite measurements aren't quite enough. Planet Earth podcast presenter Sue Nelson met members of the Natural Environment Research Council's Airborne Research and Survey Facility and spoke to pilot Carl Joseph.
What makes this aeroplane special is that it was actually manufactured as a scientific platform. So instead of really actually fitting the cabin area with seats, we've got a 2-metre hole or 2.1 metre hole in the floor that allows us to put a load of scientific instruments in.
Well, one of the crew members is James Johnson, who's an instrument operator. What instruments do you actually operate on board this plane?
The instruments that we're going to operate, which is the main core suite that we have on board, are the LiDAR, the light detection and ranging system, and the Eagle and Hawk sensors, which are hyperspectral systems looking at shortwave infrared and very near infrared.
Well, let's go on board the plane briefly before we take off. Small steps. Oh, it's quite narrow, isn't it? It's
yes,
less than a couple of metres across, and we're both having to stoop.
The instrument down the end there, the sensor that you can see there, that is the LiDAR, which basically...
The silver box.
The silver box at the end there, yeah. That will produce a digital elevation model of the ground. So it's a laser that fires down to the ground and we pick up the return and can actually map the ground and see the contours of the ground.
And what would that information be used for?
I suppose that they would use that information for looking at various different things such as erosion. You can see that the difference that something has moved, for example, a glacier. You can actually see from 6 months ago, if we've surveyed a glacier in Iceland or Greenland, you can then go back and do another LiDAR survey and you can see how it's changed, its features have changed over a period of time.
Now, in front of the silver box, the LiDAR, we've got a bigger, sort of an old-fashioned 1990s stereo, really, looking, isn't it? Like a stack of black boxes.
Yes, that is the hyperspectral system. So what that does is looks at the ground again, and it looks at it in the shortwave infrared and the very near infrared bands. So it's not looking at what you can see with your eyes specifically. It's looking at, for example, yes, that's a green leaf, but what kind of green is it? Is it an oak tree? Is it a beech or something like that?
That can tell the difference?
Yeah, you can look at stuff like that.
Good grief. Now, the pilot, Carl, said that there's a hole in the middle of the aircraft, but I can't actually see that hole. Is that because this instrument is placed over the hole?
Yes, all of these instruments are placed over the trench that is in the middle of the aircraft. There's no danger of anything or anybody falling out.
Well, I'm very glad to hear that, because we're about to take off to do a calibration flight.
Yes,
is that right?
Yeah, that's correct. What we're actually doing here is we are checking the instrumentation, checking it is working.
Sierra Alpha, contact 5125.250. Maybe historic parts radar, pass message. Maybe historic parrot chipmunks, total 4 POB.
Well, we're several thousand feet above southwest England now. Rather unusually, we're sat with our backs to the pilot instead of facing the direction of travel, which I must admit, even for somebody like me who loves flying, it's not that great on the stomach.
That's right, I know what you mean.
And you've got 6 computer screens in front of you, as well as a sort of more mobile, flexible one in front of me, where we can see the ground beneath us.
Basically, what we have here is the webcam, so this is a continuous reel of all of the ground that we're flying over. And then the LiDAR, we have the LiDAR controls, which is a laser that's firing to the ground and taking a elevation model of everything that we are flying over. On these screens here, one of them is the Eagle, which is one of the hyperspectral systems on board, and the Hawk. And as you can see, as we're going across the ground, it is looking at what we are flying over.
Okay, do you want to close the door, James?
Closing the door.
Flaps coming up, Dave. Remote sensing missions can last up to 5 hours, but all the information collected helps fill the gap between what scientists can obtain both from satellites and on the ground. Pilot and electronics officer David Davis.
There's a lot of work completed post-flight by our data node in Plymouth Marine Laboratory.
So it's not just land use, glaciers, climate change, it can be oceans as well?
Yeah, we can cover everything from marine, archaeology, geology, ecology and anything in between. So if the scientists can think of a good project for it and put their application in, providing their science is graded to a high enough standard, we will fly it.
David Davies, James Johnson and Carl Joseph from the Airborne Research and Survey Facility talking with Planet Earth podcast presenter Sue Nelson. You can find out more from Planet Earth online if you follow the links at nakedscientist.com/Planet Earth. You're listening to The Naked Scientists, and this week we're talking metallurgy and the materials of tomorrow. Still to come, we visit the Rolls-Royce precision casting facility where they make the components that keep us airborne. But first, with a historical perspective, we sent Mira out to the blacksmiths to discover the science that underlies this ancient art.
For this week's Naked Engineering, I have a new partner in crime. It's John Averson, a research student from the Materials Science Department at the University of Cambridge. Now, John, this week we're going to explore kind of ironworks and metalworking.
That's right. Even though ironworking has been done for about 4,000 years now, it's only in the last 100 years or so that scientifically we've kind of understood exactly what's going on during all of the processes. So the art of the blacksmith is really to take a piece of metal and do a series of processes to it to give you the shape that you want, but also the properties that you want. And that really happens by controlling the structure really down to the atomic level.
So to see this in action, this week we've come along to meet Gordon Bevan, who's a blacksmith based in Eltisley in Cambridgeshire.
We make gates and railings, fire grates, anything to do with ironwork.
And well, today you're going to be making us a chisel. What are the main requirements of a chisel?
We're going to form the material into a chisel shape, and then we're going to harden it and then temper it.
So basically, once we've heated it, then it gets really easy to form into a certain shape that we want, because materials just tend to get softer the hotter they are.
Moving over to the forge now, what's the actual material burning underneath it? So what's the fuel?
It's coke.
Coke's just sort of coal that's been treated to remove things like sulphur. Putting a load of sulphur in the iron would be really, really bad news for the properties of the workpiece.
You've got a piece of metal heating up here in a bright orange flame, but what metal is this?
It's a piece of tool steel.
Tool steel is just an alloy of iron and carbon, fairly small amounts of carbon in there. What makes it particularly good is that if you keep carbon contents low in iron, then it's possible to harden it really, really well without having the sort of brittleness of cast irons and other sort of higher carbon content steels.
So Gordon is just pulling the metal out now, and the end of it is bright orange, so it's just burning hot. What temperature must it be reaching, John?
It must be about 900 Celsius, like really, really high temperatures.
And so what are you able to do with the metal at this high temperature, Gordon?
The oranger it is, or white, the softer it goes, so it's easier to hammer. Now when I hammer it, it's going to be easier to handle.
And John, what about the metal then makes it so extra kind of bendy and I guess malleable at such a high temperature?
Well, there's two things. Atoms are just moving around lots faster at high temperatures, so it's really easy to slide them past each other and permanently deform the material. But also, iron's got this really, really unique property that at about 700 Celsius, it transforms from being one crystal structure to another. And the higher temperature crystal structure is a lot easier to deform. So there's two real reasons why it's so good to work it so hot.
Hence why I guess when Gordon's hammering it into shape here, the end has become quite nice and flat and sharp now.
Yeah, exactly.
What's the next step? You've heated it and you have bashed it pretty much into the shape you want.
We're now going to harden it. We're going to quench it in some water.
So you're just dipping it into what just looks like it's a bit dirty water, it's a bit murky, it's brown, but it's not like it's even ice cold water, it's just simply room temperature water that you're dipping this into.
That's right. It's probably warmer than room temperature because it's standing by the forge.
So a minute ago this was reaching up to 1,000 degrees or something, and now you're just handling it.
It's now hard and cold,
So what has made it become hard simply by dipping it in this water, John?
Iron, and especially iron carbon alloys, have this remarkable thing that when you quench them down from really high temperatures, like 1,000 Celsius that we saw before, they form this crystal structure called martensite. It only happens when you cool things down really, really quickly. And this structure is really, really hard to deform, hard to bend, but it also is ridiculously brittle. So if you were to hammer it or to bend it or something, it would just shatter straight away.
So Gordon, you've made it malleable, bendy, and knocked it into shape, hardened it by dipping it in the water. What's next? It's starting to really look like a chisel.
I'm just going to clean it up now on linisher, sharpen the end, and then it'll be down to getting it hot again and tempering it.
You've placed it back into the forge now, and one of the reasons you've just cleaned it up is so you can see the colours at which it's burning.
That's right, so I can see the colours. It should go straw. If I go past straw, it will go to the blue, which will be too soft, so I need to stop it before it gets to the blue stage.
And this is all the end of the chisel, the bit that you've actually worked.
Yeah.
The fact there are different colours gives us like a natural thermometer to tell us, just by eye, how hot the steel is. We want to get a mixture between the hard, brittle martensite with the much softer but much more ductile and malleable low-temperature iron structure. Just by judging the temperature, we can choose the mixture that we get between those two different types of crystal. That locks in the final properties of the tool.
So as Gordon mentioned, he doesn't want it to get to the blue colouring, which is far too hot, and so is that therefore too malleable?
Yeah, that would end up too malleable. Too much of the martensite would disappear, and so it wouldn't be hard enough to be a really useful tool. It's this last step that really locks in the properties that give the tool what it needs to do its job.
So looking at it now, it's got that straw colour, which is what you wanted, but there is a bit of blue, and so you've pulled it out now. Is that now just to cool it down a bit to stop it being that blue?
Yeah, I'll stop it when the tip gets to the straw colour, like it's getting straw now. So now I've got to cool it off.
Interestingly, this time to cool it, you haven't dipped it into kind of room temperature water, you've dipped it into a box of oil.
Used oil. It's slightly better than water.
The oil will take the heat out of the tool a lot more slowly, and so we can really lock in the crystal structures that we put in by just picking the colours perfectly on the tool before we quenched it. It's a lot more gentle and it's a lot nicer process to the poor bit of metal.
Okay, so Gordon, you're just pulling that out now, and I don't really want to touch it, it is covered in oil.
Just got to be wiped off and then we'll try it. Yeah, it's cold now, so we can try it on the side of the anvil, see if it'll cut.
Is it any good?
It's not shattered and it's not dented, it's perfect.
So just using the skill of a blacksmith, Gordon's managed to control the atomic structure of a piece of iron to be able to cut another piece of metal perfectly. It's really, really amazing skills.
Cambridge research student John Avison and blacksmith Gordon Bevan explaining the art of metalworking to Mira. Mira's also made a video of that trip to the smithy, and you can see it at nakedscientist.com/engineering. Now, back to Diana.
We humans have been moulding metal to our will for at least 3,000 years. In fact, our use of metals marked the beginning of the aptly named Bronze Age. These days, we fine-tune the properties of metals to perform in extreme circumstances, inside nuclear reactors, jet engines, rockets, etc. To find the right combination of properties, we rely on metallurgists like Howard Stone at Cambridge University's Department of Material Science and Metallurgy.
Well, one of the first things I don't think people often get much an appreciation for is the fact that metals are actually crystalline materials. In other words, if you look at them on a very microscopic scale, at the atomic scale, you'll see that the individual atoms are arranged in a very precisely defined periodic array or pattern. What you have to imagine if you were looking at your piece of cutlery or the tip of your ballpoint pen or even the legs of your chair is that the metal itself is built up of all these little individual crystallites, exactly analogous to grains of sand on a beach or sugar in a bag of sugar. Only that there is no space between the grains. It's all been, if you like, pressed together so that there's no distance between these little individual crystallites.
But not all of the crystals in any given metal will be the same.
The individual crystal structures, the different arrangements that can be adopted by these metals, have a profound influence upon the properties of the materials. And the presence of these phases as we refer to them, in other words, regions of material which have these different crystal structures, does have a very important influence on the properties of metals themselves. It's our role as metallurgists to work out what the best possible combination of phases we can get at a material is, and therefore the best possible set of properties that we can possibly achieve.
One way to alter the crystal structure of a pure metal is to add other elements. Steel, for example, is a mixture of iron and a small amount of carbon, but its properties are surprisingly different from both original materials.
If we add any other element to any given element, a metallic element, so if we, for example, add carbon to iron, then we might expect to form new phases. In steels, we can expect a whole series of carbides as a possibility. And the morphology and crystal structure of those individual carbides can be very different depending upon the conditions in which it's been processed and also the presence of other alloying elements. And that will have a very profound effect upon the properties of the resultant material.
These mixed metals, or alloys, may be able to perform a given task far better than the pure metals, and as such are found all around us.
Well, if you look at your average piece of tableware cutlery, you're probably looking at a steel, so an iron-based alloy, which contains significant quantities of principally chromium and nickel. If you look at an aeroplane, for example, most of the airframe will be made of aluminium alloys. The engines themselves may very well contain far more exotic things like titanium and nickel alloys as well.
For extreme environments like the high-temperature, high-torque conditions inside a jet engine, we turn to a subset of alloys called the superalloys.
Nickel-based superalloys justifiably deserve their name because they're the only class of materials that are able to operate at the combination of very high temperatures and very high stresses whilst maintaining their surface stability, i.e. not being degraded too badly by the environment in which they operate.
But what is it that makes these particular alloys so good?
They're based principally on a combination of nickel and aluminium. So nickel is an element which adopts a face-centered cubic structure. In other words, if you looked at the atomic scale, you would see the atoms arranged in more or less like little cubes, with the atoms on the corners of those cubes and the one in the middle of each face. Now, with the addition of aluminium, the alloy will form precipitates, in other words, an additional phase which comes out of the material, embedded within the material, which are Ni3Al. In other words, for every 3 nickel atoms, you'll find another aluminium atom. And they adopt a very precise crystallographic arrangement relative to each other. If you imagine my little cube again, I will have aluminium atoms on the corner of the cube and now nickel atoms in the face of each cube. Because of the similarity of that particular crystal structure with the nickel itself, these precipitates are able to form in very good registry with the matrix in which they form. And this creates a real barrier to motion of atoms past each other through the crystal structure and really resists deformation at very high temperatures.
Making the most of superalloys can involve adding small amounts of very exotic metals, which can improve the properties, but, as is the case with exotic things, this comes at a cost.
Well, over the last 50 years, we've done everything we can as metallurgists to improve the properties of nickel-based superalloys by considering all the possible alloying elements we could reasonably include. Commercial nickel-based superalloys for turbine blade applications, for example, now can contain 9, 10 or even more elements in very precisely controlled quantities to get optimal properties. Some of the latest elements we've considered include things like ruthenium, which is a very rare platinum group metal, and that has extended the temperature capability that superalloys are now able to operate beyond those of previous generations. But these are very rare, very expensive elements. The real challenge for us is to identify whether there are any other alternatives to nickel-based superalloys. And that is a challenge which many people have been investigating over the last 50 years.
That's Howard Stone, Assistant Director of Research at the Department of Materials Science and Metallurgy at Cambridge University.
Laying the facts bare. The Naked Scientists.
You're listening to The Naked Scientists. I'm Chris Smith. If you've been on a flight recently, then there's a very high likelihood that you were carried aloft by a jet engine. These work by compressing air and squirting in fuel, which then burns, expands and generates thrust. But this also creates one of the harshest imaginable environments inside the engine, where the gas stream routinely exceeds 1500 degrees Celsius. That's well beyond the melting point of standard metals. To withstand this takes specialist superalloy components, which are produced with very high precision. And to find out how they're made, Ben Valsler's been to the casting facility of one of the world's top jet engine manufacturers, Rolls-Royce, in Derby, where he met Paul Withy.
I'm the casting specialist for Rolls-Royce, and this facility is the precision casting facility in Derby. It's Rolls-Royce's largest foundry, and it makes turbine components for large civil engines and military engines. This is one of the single crystal facilities in the world, which is one particular branch of precision casting that makes only single crystal components. And the benefit from an aerospace perspective is that if you take out all the boundaries between each of the crystals, you get the strongest possible metal that you can. And that's really needed in the hot part of the engine. So like a sugar cube, when you crush it, you actually don't break each of the individual grains, but you break the boundaries between the grains. It's the same in an aerospace metal. So we make single crystal components to get rid of those grain boundaries and have the strongest part we can.
So what's the actual process? How do you go from raw metal to jet engine parts?
There's a number of different stages. If you imagine the component as not being a solid component but being a hollow component, we have to make a ceramic model of the hole we want. So we make that component called a core, inject wax around it, so we end up with a wax model of the component with the hole in the component filled with ceramic. And we take that model, we'd go into what we call the shell room, where we actually cloak it or clothe it in ceramic, and then we'll replace the wax with the metal, and then there'll be the solidification process that's the heart of this process that means we can grow a single crystal. We have to pour in a vacuum, so everything is hidden away behind steel walls.
Could we have a look anyway?
Of course, let's go. This is what we call the wax room. It's a room in which we take the initial ceramic cores that we talked about earlier, and we're going to inject the wax around them. The room is a mixture of wax injection machines, where we're actually putting the steel dies in there and injecting the wax into the shape we want, and assembly benches, where we're taking those wax shapes and putting them into the orientation on the runner system that we need for the further processing of the parts.
So now can we follow some of these wax structures through into the next stage?
Of course we can.
We've come through a large door and into the second stage. The last room was very warm, it smelt of melted wax. In here it feels a lot colder, but it's also a lot noisier. What happens in here?
Well, this is the shell room. It's actually no colder. It just feels colder because of the controlled humidity, but actually it's held at exactly the same temperature, so the wax is exactly the same size in one room as it is in the next. And what we're going to do is take those wax assemblies, we're going to clean them, wash them, and then we're going to dip them in a ceramic slurry, and then take them out, drain them, and then sprinkle grit on them, and then allow them to dry for a couple of hours, and then bring them back and do the whole thing over and over again, up to 10 times.
So the slurry is sort of the sandy stuff that will turn into your ceramic layer?
It's actually a liquid that actually has a bit of a ceramic glue in there called a silica sol that will allow that all to stick together, and the bulk of it is delivered as a gritty, dry sand sprinkled on top of the wet surface.
So how thick a layer of ceramic do you end up with?
It's normally somewhere in the region of about 5 millimetres.
And where do we go to next?
The next stage of the process is to take the wax out and then move on to casting.
So the wax moulds are now invested with their layer of ceramic, and we've come through into a very, very warm room. What happens in here?
This is the room where we take the wax out, we wheel the moulds in, we close the door, we press the button, and in 4 to 5 seconds we inject superheated steam at 180 degrees C, which allows the wax to melt out really quickly. The wax doesn't melt as a whole, it only melts on the surface and doesn't conduct heat well. If we did it slowly, the wax would expand more than the shell could take and we'd blow the shell off the outside. So this way we get the wax out without breaking the shell.
And now we're actually left with a ceramic mould that we can then pour metal into.
We now have a mould with a core in the middle of it held in space that's now ready to cast.
And now, with the ceramic layer fired, we actually get through to the bit that involves molten metal, the bit that most people think of when you talk about casting. It doesn't look like I would imagine it would. I can't see these rivers of molten metal.
The whole point of this process is we control it as much as we can, because we have to take that mould, we lock it onto a copper-cooled chill at the bottom, and that allows us to have a very cold end of the mould. We then push the whole mould up into a chamber that's at around 1500 degrees C, allow it to bake there for about 20 minutes, and then we melt a charge in a crucible above that, pour that charge into the mould itself. The mould at 1500 degrees C is above the melting point of the metal, so most of it stays molten, except for the last little bit that hit the copper chill and then froze, as lots of different grains, all orientations, hundreds and thousands of grains. We then take the mould and we draw it into a cold chamber, so there's a temperature gradient from hot to cold, and those grains all start to grow. It just so happens that the grains that grow the fastest are also the grains in the orientation we want for mechanical properties purposes. So by a natural selection process, they grow really quickly, upwards and sideways, and kill off all the other grains.
So you're getting a single crystal because that one crystal structure happens to just be a bit more stable and perhaps outcompete the other crystal structures that could form.
That's correct.
So how long does it take for this single crystal structure to form?
It takes just over an hour to make a single crystal component of the size that we tend to manufacture. And that's for the large civil engines of a component that's about 10 centimetres to 15 centimetres tall.
So once they've been poured, once they've had chance to set, where do we take them now?
They then move to the back of the facility where we'll cut off each of the individual components and then use a strong alkali solution to remove the core, which then leaves us with these castings with the right hollow inside them in the right place.
So once the products have come through, they've cooled, they've had all the bits of excess cut off, how do you check that they are what they need to be?
We have to check that they are a single crystal, and we'll do that by dipping them in acid and then looking at whether there's a grain structure there, and if there isn't, we've got a single crystal. We'll also check using X-rays to see whether they're the right orientation of crystal. We'll use gauges to check that the external profile is correct, that the length is correct, and that they're all the right tolerances. We'll also use a dye penetrant to look for surface defects, and we'll use X-rays to check for internal defects.
And how perfect do they need to be? What error margins do you have?
In terms of the crystal orientation, we've got a few degrees on orientation that we need to hit. And in terms of dimensional requirements, the drawing usually requires us to be within 0.1 or 0.2 of a millimetre of the required position. And so we'll check every blade to those kind of dimensions. And unlike certain industries where you can sample inspect, once we've got a metal part, every part goes through every inspection operation. This is one of the finished blades, and this has actually gone through the next stage of the operation, which is machining and the drilling in of the film cooling holes into the internal core passage. It's about 12 centimetres tall, and it survives the really high temperatures and pressures and stresses inside the engine.
What conditions could that piece of metal now put up with?
Well, this turbine blade itself will face conditions of the gas stream around it when the engine's operating being 250 degrees above the melting point of the metal. And the stresses when it's spinning round at about 10,000 revs per minute is the equivalent of hanging a lorry off the end of it in a static case. This blade then has to take 750 horsepower or more out of the hot gas stream to power the upfront parts of the engine. So each one is about the same horsepower as a Formula One car. That gives us a component that will last more than 5 million flying miles and is quite an arduous environment to live in.
Paul Withy taking Ben Valsler around Rolls-Royce's precision casting facility in Derby. And Rolls-Royce reckon that at least 200,000 people around the world are being held safely aloft by their engines at any moment in time. In other words, right now.
Bringing the facts to bear. The Naked Scientists.
You're listening to The Naked Scientists, and I'm Chris Smith. Now, we don't all have access to a forge or a precision casting facility, but Ben and Dave have a way to do some simple metallurgy at home.
We thought we would do a very special extra kitchen science this week to show you how you can change the crystal structure of metal at home. So Dave, what are we going to be playing with?
Paper clips. They're a nice sort of a nice small piece of iron, so we thought we could play with those. So if you get a paper clip and then straighten it out.
They're actually really quite tricky to straighten out. You can sort of straighten out the big bends, but there's still a kink left in there.
If you bend virtually any metal, it actually gets harder. This is because a metal is a crystal, and in order to bend it, you've got to reorganise that crystal. crystal's a repeating structure, and if you wanted to shift a whole line of metal atoms, it would require an immense force. So actually the bending happens at little defects, they're called dislocations. They're sort of analogous to a ruck in a carpet. And if you imagine a ruck in a carpet, if you push that all the way across the carpet with quite a small force, you can move the whole carpet across by a couple of inches. But the problem is, if you bend too much, pairs of these dislocations can crash into each other, and when they crash into each other, they lock up, and that means they can't move anymore. So the more you bend a piece of metal, the stiffer it gets because there's fewer dislocations to move.
That's all well and good, but bending paper clips doesn't seem like much of a kitchen science.
So now we're going to try and do some real metallurgy to it. We're going to heat it up in just a normal gas stove flame. You could use a blowtorch as well. You need to be able to get it up to red hot.
So if we're handling red hot metal, even something as small as a paperclip, we obviously need to be quite careful. I can see that you're going to hold it in a pair of pliers just to keep your hands away from the flame. And very quickly, actually, it started to go orange, and that's glowing bright orange.
And now for this one, all I'm going to do is take it out and let it cool down. Very quickly it stops glowing orange, but it's going to stay hot for a long time after that. So once it stopped glowing, leave it a few seconds, then put it down somewhere which doesn't mind a hot thing on it, and just leave it there literally for a minute. That way you can be sure you're not going to get hurt by it.
So while that one's cooling, what else can we do?
We can actually do another different piece of metallurgy, a similar experiment working on a different principle. I'm going to heat up another paperclip, again to orange hot. I'm now going to plunge that very quickly into a little glass of water I've got ready before. We'll come back to that later.
Let's go back to the first bit of metal. So we heated this up to glowing orange, and we've left it to one side to cool down until it's handleable.
Now what I want you to do is try and bend the two ends, the end which hasn't been heated and the end which has.
Okay, well let's start with the end that hasn't been heated. It's pretty stiff, but I can definitely bend it. So now I go to the one that has been heated and cooled down, and that's really soft. I can bend that far more easily than I could the unheated end.
We were talking about the metal getting stiffer as we bend it backwards and forwards because of these dislocations locking up. When you heat it up, that gives the metal atoms huge amounts of energy. These dislocations can move past each other, no problem. They actually randomly move around in the metal, and you completely sort of reset the clock and set it back to zero. If you let that cool down slowly, you've got lots of dislocations in there, they're not locked up. So it's really flexible, and you can bend it backwards and forwards until it work hardens again and gets stiff.
So that's one effect that we've seen from heating it and then allowing it to cool quite naturally just in the air. But the other one we quenched. So this got cooled down very quickly.
Okay, this is using a slightly different effect which the blacksmith was using earlier in the programme to harden his chisel. When we heated up the paperclip above 700 degrees centigrade, its atomic structure completely changed. It went from a body centre cubic structure, where all the atoms are arranged sort of like on the corners of a cube with one atom in the middle, to a face centre cubic structure, which is atoms on the corners of all the cubes and one in the middle of each face, like a 5 on a dice. If you cool it very, very quickly, it changes structure so quickly, you actually end up with a completely different structure. It's called martensite. It's a horrible, messy crystal. It's incredibly brittle. So if you feel that now, you should find that the end which was heated is quite stiff.
That's actually made quite a significant difference to the sort of mechanical properties of the metal.
Yes, and if you wanted to alter the properties of something at home, say you were trying to bend something through a large angle, you could heat it up and cool it slowly in a annealis and it would carry on bending. And so you can actually use metallurgy at home just like this.
Ben and Dave explaining how to change the crystal structure of a paperclip using just your gas hob. And as we come in on the final approach towards the end of the programme now, Diana is blowing hot and cold in this week's Question of the Week.
This week, how to warm up in the cold.
Hi, Naked Scientists. My name is Paul from Atlanta, and my question is this. How come commercial airliners and many other airplanes get very cold surfaces when flying, and re-entering spacecraft and many supersonic jets get very hot surfaces? At what speed does the wind chill effect give way to the heating effect? And how fast would I need to ride my bicycle through cold weather to maintain a room temperature?
Let's tackle planes first. Why do shuttles get so much warmer?
I'm Kevin Knowles. I'm Professor of Aeromechanical Systems for Cranfield University, and I work at the Defence Academy of the UK in Shrivenham, Oxfordshire. In essence, the answer to the question is that aircraft wings are cold because they fly high in the atmosphere, the region known as the troposphere, and atmospheric temperatures fall with altitude in the low atmosphere. So an aircraft flying at about 10 kilometres, which is typical above the ground, on a day where it's only 15 degrees Celsius at sea level, will be experiencing temperatures of about minus 50 Celsius outside. If, however, you move fast enough in excess of the speed of sound, then there's a significant kinetic heating effect, and that's what spacecraft experience. For example, if an aircraft were, again, flying at 10 kilometres altitude, but now at nearly 7 times the speed of sound, then the temperature that it would feel due to this kinetic heating, the highest temperature would be about 10 times the ambient temperature, but measured in degrees Kelvin. Now, 10 kilometres altitude, the temperature in Kelvin is 223, so our Mark 7 spacecraft would experience 10 times that. So its peak temperature would be 2,200 Kelvin, or about 2,000 degrees centigrade. At 10 kilometres, those two effects balance out if you're flying at about Mach 1.2. So at that speed, the kinetic heating is just enough to bring the peak skin temperature up to sea level temperature.
So it's not so much the wind chill effect as the fact that planes fly around in a colder part of the atmosphere. Travelling at Mach 2, Concorde used to experience surface temperatures over 100 degrees Celsius, causing the fuselage to extend by as much as a foot. But what if you're a cyclist?
Hello, my name is Holger Babinski and I'm Professor of Aerodynamics in the Engineering Department of Cambridge University. How much friction you need to compensate for the fact that the air is cold around you depends very much on the temperature difference between your body temperature and the air temperature. You asked how fast you would have to cycle, so I shall assume that you're cycling at sea level. And there, the surrounding temperature on a cold day might be something like 17 degrees. And in order to generate enough friction to bring the air up to body temperature, you have to cycle at about 63% of the speed of sound. With the speed of sound at sea level, that is pretty much 480 miles per hour, so you have to be pretty fast to achieve that.
So a few jetpacks might help. On the forum, Diver John recommended that you try covering yourself in Vaseline to keep warm next time you cycle, although you may slip off the saddle. Next week, why does cereal always set like rock?
My name is Steve Slack and I'm from Hampshire in England. My question is about Weetabix. I love my Weetabix in the morning, but if I don't clean the bowl straight afterwards, it sticks like glue and won't come off. Why?
What is it that makes breakfast foods stick to the bowl and require crowbarring to remove? Answers to chris@thenakedscientist.com. You can Facebook us, you can Twitter us with @nakedscientists, or you can use the forum, and that is at thenakedscientists.com/forum.
Thank you, Diana. That is it for this week. Thank you to Johnny Hudson, John Avison, Gordon Bevan and Paul Withy for their insights. Next week, we're answering your science questions for you, so send them in, or any other thoughts or feedback. The address chris@thenakedscientist.com. You can also tweet @nakedscientists or write on our Facebook wall. That's at thenakedscientist.com/Facebook. Until then, thank you for listening and goodbye.
The Naked Scientists comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC, the Natural Environment Research Council and UK FAST. For more information, look us up online at thenakedscientists.com.